Hi everyone, thanks for the opportunity. I'm presenting today a new term of hydrogen energy, which is the new era for a new kind of economy. So hydrogen economy is getting bigger and bigger very quickly. So I'll go over the hydrogen economy, just a general kind of information, technical information. And if there's any questions, you can stop me or leave it to the end, please. So as we know, global warming is all blamed on the use of fossil fuels. And because economy depends on energy, then we are now in the middle of the fossil economy. And the global warming always blamed on our dependence on fossil fuels. Also, the energy security and the price fluctuation, it's all very high in all political agendas around the world. And there's a growing awareness of this global warming and the pollution and the carbon dioxide exceeding 400 particles per million. And also there's some international obligations these days, like the Kyoto Protocol and the national determined contributions. So we are shifting away from the fossil energy towards something a bit cleaner. And it's obvious that renewable energy is going to play the main role in this transition towards a cleaner economy or cleaner energy in the economy. It's obvious that most of the renewable energies got a very specific challenges. They are variable and intermittent. Some of them not, like the geothermal, but mainly the solar energy through the PV or through the concentrated, and the wind energy, even the ocean energy, it's always variable and intermittent. So as we see here, there's always up and down, and sometimes they are not there. So obviously we need a storage system, like a battery, to shift the energy from when it's available, more than what we need, to where we need it. But the question is, we are talking about economy and economy of scale, then how big is those batteries should be? The size of the batteries, the cost of the batteries, and how long we can keep the energy in the batteries. We call it the discharge duration. Batteries can do the job up to a certain percentage of penetration into the existing energy systems. After that, you'll pay cost much more every 1% going up than probably the first 50% of if you want to store that energy. Now, we have hydrogen, which is the most abundant element in the universe. And we are made of carbon and hydrogen, everything almost. The problem is we cannot find it in a pure way, like in a pure form of that element on Earth. So we need to put some energy to produce the hydrogen. And that means hydrogen is an energy carrier, not an energy source. So we put some energy, we store it in that hydrogen. Hydrogen is just a very simple and light element, one electron, one proton, colorless, odorless, but very flammable gas. And the atomic weight is around 1.008. And this one 2008, they read it in the US as the 8th of October, 8th of 10. So the 8th of October every year, they were celebrating the last 7, 8 years, celebrating this as a hydrogen day in the US. Actually, last year, we brought that to Australia, and we celebrated at the 8th of October last year for the first time outside the US, here in Australia as a hydrogen day, and we repeated that last October, 2020. So why hydrogen? When we have excess energy, we can store that energy, as we said, in the batteries, but the good idea is to convert that energy to a form of gas, and in this case, hydrogen. And hydrogen, once you have the hydrogen, you can generate all different types of energy straight away, like heat energy, electricity. You can use it as a direct fuel. Very easy to integrate into the existing energy systems and transport systems. You don't need that instance balance like the electricity. When you generate it, you have to consume it. You can store the hydrogen. It's storable, exportable, transportable. So it's so much easier to deal with in that large scale of energy storage. Now, one of the most important things is the discharge duration for the hydrogen. It's comparably similar to the methane. So they are both gas. And if we compare that to the flywheels or the batteries, compressed air, even pumped storage, it can go much bigger and can last for longer. So longer discharge duration. And you can also discharge to 100% depth of discharge. Not like the batteries, you cannot consume what's in there. And one more important thing is the batteries, when they are full, you cannot do much. But in the hydrogen, you can store that hydrogen or convert it to another form of energy storage, like convert that to ammonia, or you just add tanks and store that one. And we'll talk about this later on. So that's why we are heading towards the hydrogen. Just to give you a quick idea, hydrogen, well known for the last 250 years. The first time was 1761, though like 15 years later, someone else, which is Henry Cavendish, was named the discoverer of hydrogen. So 15 years after the first one, which is Robert Boyle. Then hydrogen was gaining like potential, and they start producing hydrogen after that. And the first time hydrogen was named and given the name hydrogenium from the Greek root hydro, which is was in 1788. A few years later, the first water electrolysis was tested, and about 40 years later, the first fuel cell actually was built and tested. Then another 40 or 50 years, hydrogen was liquefied for the first time, and just about in the 1900s, that was the first time they used hydrogen in big balloons. And between 1920 and 30, there were a lot of those airships to cross the Atlantic carrying passengers, and that was filled with hydrogen. Now, after that, NASA employed liquid hydrogen as a fuel for the first time in 1961. But 20 years later, they launched the first shuttle using liquid hydrogen. And in 1988, there was a plane, actually jet fighter plane, Russian one, was fueled with fuel hydrogen. And since that date, it started getting very quickly the momentum. Well, every time you mention hydrogen, the people always remember the Hindenburg, which has happened in 1937. It was a disaster. Though hydrogen was not blamed for this, but even further, if you mention hydrogen, some people, they think about the hydrogenic bomb. And it's completely not related. So accidents happened and delayed a bit the deployment of hydrogen in the energy sector. But how safe is hydrogen? Hydrogen is, first of all, non-toxic, which is a good thing. It's much lighter than air, so it dissipates so quickly. If an accident happens, if there's an open space above, the hydrogen will go so quickly and burn at once instead of spill over the place and take the fire around the area. So kind of much safer compared even to LPG. If an accident in a car carrying LPG happened, then we'll spread the fire to all the cars and the things around it. But with the hydrogen, you hear a loud bang, but actually not more than that. That's it. So comparably, it's a fuel and got some sort of danger with it, like all other fuels. There's kind of some special engineering controls required, especially for the metal embrittlement from the hydrogen. And so we are learning more and more and quickly these days to overcome all these challenges. So the more hydrogen demonstrations gets underway, then the more we know about how to deal with it safely. To have a quick idea about the hydrogen value chain, so basically it's three parts. One of them is when you produce the hydrogen, which could be, there's so many different pathways and so many different types of energy you can apply to produce hydrogen. And then once you have the hydrogen, you have to think about how you're going to store it. Then the hydrogen can be utilized in so many different ways, like direct fuel, generate heat, generate power, as a chemical raw material in the refineries, even deal with the bio-waste, etc. We'll talk about this a bit more. Now, as we mentioned, because hydrogen is an energy carrier, despite that, when you utilize the hydrogen, when you use it, there's no emissions. The byproduct is just water. You burn it or oxidize it, will be just water. But we have to think about the energy already used to produce the hydrogen. So if you are producing the hydrogen using fossil fuel energy, then that hydrogen is actually carrying that pollution with it indirectly. Well, when you use it, it's zero emissions. So there is about three types, main types, but there's so many others. One of them is if we produce the hydrogen from fossil fuel, we call it gray hydrogen. And this is represent 95% of the market, existing market. And the existing market around 80 million tons per year. This hydrogen mainly used as a chemical raw material to produce fertilizers, ammonia fertilizers, and in the refineries and so many other things. Now, nowadays, we start developing technology to capture the carbon of this process. And if we capture the carbon and store it or utilize it, we call it blue hydrogen. But if we use pure renewable energy via water electrolysis, we call it green hydrogen, which is nowadays represent about 5% or more. To give you an idea about those pathways, so Energy could be electric, photo energy, biological, chemical, heat. This energy applied to hydrogen-containing materials, like water or any hydrocarbons, using a certain technology. In the presence of catalyst, then you get the hydrogen. So as we said, we're going to focus now on the renewable hydrogen. So renewable electricity via electrolysis, then storage, then utilize it. To have a quick overview over the water electrolysis, it's when you apply a DC current into the water via 2 electrodes in the presence of catalysts, then you get the water to be split to oxygen and hydrogen. You'll get double the amount of moles from the water as a hydrogen compared to the oxygen. There's main 3 types of electrolysis: alkaline electrolysis, proton exchange membrane, and solid oxide electrolyzers. They are a bit different in the technology itself. If we have time, we'll go a bit more in that. And to have an idea how much water we need, we actually need about, if we are using a PEM electrolyzer, we need about 15 liters of raw water per 1 kilogram of hydrogen. If it's a pure deionized water, it's about 10 liters per kilogram of hydrogen. To give you an idea, 1 kilogram of hydrogen can store 33 to 39 kilowatt hour. So, which is enough for 2 houses, 24 hours. You need just 10 liters. So it's not much water. And you can claim, if you use it through a fuel cell, you can reclaim some of that water, actually. You can reclaim 100% at a very advanced stage. So you probably won't need that much water. This is how it works. You put the DC current, then through the membrane, the water will split to oxygen and hydrogen. And it depends on which ion going to cross the membrane, if it's the oxygen or the hydrogen or the hydroxide, like the OH, that's determine the type of electrolysis. Now storage. Storage is kind of another challenge. Hydrogen can be stored in a physical-based system like compressed gas or like liquefied, like you liquefy that gas to liquefied or liquid hydrogen. You can cool it down to, with compression, you can also use underground storage. If you use one of those depleted salt caverns, the depleted gas fields or salt caverns, you can store hydrogen there. Or you can store it as a compressed gas using those cylinders or bottles. The new technology is start developing so quickly. It's a material-based type of storage. So we use absorbing or adsorbing materials. It's like a sponge and absorb some of the water. And those ones actually gaining momentum now. We call it solid state type of storage. And probably metal hydrides, it's the most advanced one these days. Utilization, once you have the hydrogen, you can use it in fuel cells to generate electricity, or use it in gas turbines as a pure hydrogen, or blended with some natural gas, or you can use it as a direct fuel for so many different type of energy needs. This is how it works. It's like a hydrogen, it's like the battery here. So, but you store it here, and you can then generate some electricity when you store the hydrogen when you have the sun there, or the renewable energy exists. And also you can blend some of it with the gas. We call it town gas. And town gas is not a new thing. Probably up to the 70, 71, we were using town gas, which is between 60 to 80% of it hydrogen, extracted from coal. We were using this down in Fremantle and in Perth until the discovery or the extraction of the natural gas. So we were using that long way before the natural gas. During the night, it's going to work. The battery can supply a bit, and the hydrogen will be like a base load generator. So the battery there is to respond to any fluctuations or quick demands. And you can also, because you have hydrogen, you can have a fueling station, hydrogen fueling station as a fuel. You can supply it as a gas. So a hydrogen economy was first introduced in the beginning of 1970s by John Bockris. He was an engineer, worked for General Motors, and he mentioned the word hydrogen economy. And since that day, the people start thinking where we can use hydrogen. Can we use it in agriculture, making ammonia and fertilizers, green steel, green coal, lithium batteries, manufacturing, all sort of industries. And this is actually a picture from Australian Hydrogen Council last year, and it shows that hydrogen can provide energy to all parts of the economy, and that's why we call it hydrogen economy. We can use it in the industry everywhere. We can blend a percentage of it to the natural gas. Nowadays, we are talking about 10 to 20% maximum. You don't need to modify anything. You just blend some of the hydrogen with the existing gas pipelines. And you can imagine how long was those gas pipelines. So there's a possibility to store a lot of energy in a form of hydrogen in those gas pipelines without the need to modify anything. So what happened last 2 years in Australia started getting momentum so quickly. Well, the word or the work around hydrogen goes back about 20 years in Australia, and the first time they mentioned hydrogen and tested was about 45 years ago in Victoria. But the last 2 years, there was a lot of work being done, and the first Renewable Hydrogen Conference happened here in Perth in August 18, and start gaining momentum. This is between 18 and 20, a lot of reports, a lot of supporting documents, a lot of studies, researches, events, until last year, September last year, they issued the hydrogen strategy for Australia by CSIRO. So it was 10th of September 2019. And in this picture here, they show that what we said before, that hydrogen, once you store it, you can produce ammonia, then this will go to agriculture, or you can export ammonia. You can use it to blend it with the natural gas and use it as a fuel, use it to generate electricity. So this is kind of a bigger picture for the hydrogen role in the economy. And they start talking about how Australia can play a big role and become a superpower by exporting renewable hydrogen. And when you export renewable hydrogen, you are storing the renewable energy. So we are exporting renewable energy to the world. And we can be a really super exporter, superpower, and a big exporter for renewable energy and renewable hydrogen. Just this year, the government moved to the phase of commercial scale. And March 2020, ARENA announced $70 million for commercial kind of plants to produce renewable hydrogen. And just after that, May 2020, the Clean Energy Finance Corporation announced $300 million. And since that date, actually 10 more times, like funding programs and new projects came to the media, and they announced a lot happening. And just recently, a few weeks ago, 2-3 weeks ago, WA government also announced about $20 million to put some demonstration plants. Now, there's two challenges still need to be resolved. One of them is, how are we going to certify the hydrogen? How clean is that hydrogen? So the current kind of a certification scheme, which is just one around the world, based in Europe, belong to Hydrogen Europe. And in this one here, they use this color coding, green, blue, gray. And if it's from coal, it's brown. If it's from nuclear energy, they call it yellow. These sort of things. Yeah, but if we just, what I'm doing in my PhD is I'm trying to develop a new hydrogen certification scheme, because I think this color coding is not telling the full story, and it's not going to work. I'll give you an example. It's obvious that if we use renewable energy through electrolysis, it's going to be green hydrogen. If we use like steam reforming from methane and do the capture of the carbon emissions, then we call it blue. If we are not capturing the carbon, we call it gray. What if we use, of course, when we do the steam reforming, we use some energy. What if that energy is renewable? Is this bluish green or greenish blue? Or some people, they start calling it turquoise. Well, but there's no accurate information in that. We don't know what's happening. So a lot of those scenarios undefined. What if we use carbon capture and storage from the coal, getting the hydrogen from coal? So it's still undefined, and we need to find some colors. So the only scheme is they came up with a threshold of 4.4 kilogram of carbon dioxide equivalent for each 1 kilogram of hydrogen. They call that one, if it's from renewable, green hydrogen. If it's not, they call it low carbon hydrogen. Now, the right way to do it is we should be a technology neutral. So we don't care which technology, which material you have used. We care about how much pollution was associated with each kilogram of hydrogen. So the proposed model is to aggregate all the pollutions or carbon dioxide emissions associated with the materials themselves, like these hydrogen-containing materials, even water. We should care where we get the water from and how we desalinate. Are we using coal-fired power plant to power that desalination plant, or renewable energy? So all the carbon emissions here, with all the carbon emissions of the process itself as a technology, then even when we say we capture that carbon and store it, we're going to use some energy there. We should care about which sort of energy there and how much carbon dioxide was associated with it. Then we are suggesting now kind of using hydrogen as a green energy because it's zero emission when you use it. But how many stars, green stars are there? So till the 5 kilograms, probably we can consider it green. So green stars. So when we say 4.4, if you have zero emissions there, absolutely zero, then 5 stars, full 5 stars. If you have 4.4, then you'll have kind of 0.6 green star there. This will encourage the research to reduce the carbon dioxide below 4.4 kilogram of carbon dioxide equivalent. Then if it goes over 5, we go to the gray level of hydrogen. And if we go over 10 kilograms, that's absolutely black. Now, this one is, this kind of a proposed model needs to be agreed on internationally. Because without certifying our hydrogen, we're not going to be able to export any of our hydrogen. And also the domestic users, they need to know, like, we remember that you buy an electric car and you charge that electric car from a coal-fired power plant. There's no point, actually. You are just do the pollution somewhere else. So we need to certify it. Otherwise, we won't be able to sell it. The other main challenge is, should we start the infrastructure first or create the market, the offtake first? And I'll give you a very quick example. If you put a hydrogen fueling stations along, say, one of the highways, but there's no hydrogen cars, what are you going to do with that hydrogen? Who's going to invest his money on this? If you import some cars and there's no infrastructure, there's no fueling station, who's going to buy those cars? So it's very important to start the infrastructure with the market to start in parallel, simultaneously. Otherwise, we will not be able to take off. It's happening around the world. We are just behind the world because there's no one taking that first step. Infrastructure should be probably start first, but they should come up together. So that's what I have to say. Thank you very much for your attention. If you have any questions or